Hey, yo. Alrighty, I'm going to be doing pages 120, I believe, to pages 142 in our little math book. Right? I'm going to start off by looking at surface area. Right? I'm going to use an example of a cone. Right? Example of a cone to figure out the surface area of that. Right? Let me just show you really quickly what surface area is. Yeah, let's use this. All right. So I got this little base chart right here. Right? So when I say surface area, I mean the area that encompasses right this object right here, right on the outer side of this object, right. I'm not looking for the perimeter, right, or I'm not looking for the area, which is the stuff which is inside of it, right. The cubic units inside that make up this this little base charger, right. That's not what I'm looking for. I'm looking for the surface area, right? If I were to take this apart, right, each of the plates, right, I would look at the surface area, the outer side. Right? That's what I'm going to be looking at in a cone. Right. All right. So you got your basic standard cone. Right. You got your basic standard cone. Okay. Let me write out the equation really quickly for what the surface area of this cone would be. And then I will go into a little bit more detail about what each variable means. Right. All right. So that is, okay, times f, r to the power of 2 plus pi times r times l. Okay, so what the heck does any of this mean? It's just a bunch of weird looking symbols and numbers, right? Let's put some meaning behind these, okay? So if you don't know already, this is pi, right? I'm sure many of you are familiar with this. This is pi, okay? This is pi, right? This right here is the radius, right? The radius, the power of 2, right? We have pi as well, another pi. So we have we have pi times the radius to the power of 2 plus pi, right? Times radius times, right? This is called the slant height. The slant height. Okay. And it's this cone, right? It's not your generic everyday square cube, right? It has a slope. It has a little bit of a slope, right? And that is our slant right over here. And that's what this L represents right here. Right. All right, so we're just gonna use that as a basis of information going forward. All right, we're gonna be looking at now the surface area of a sphere. Now let me write up over here the formula for that, and you'll soon understand what it means as I go along. Right, so let me write that out really quickly. So 4 pi times the radius to the power of 2. Okay, so what does any of this mean? What does any of this mean? Well, let's look at an example problem. Let's look at a situation. Right? Let's say we have an open cylinder. Right? Pardon my poor art skills. Not very good over here. Let's say we have an open cylinder, right? Inside of that open cylinder, okay, we fit a sphere, right? A sphere, right? It has the same exact width of this said open cylinder, and what we are going to try to find is the surface area, right? And if I can find it, uh, surface area, the outer units that encompass an object, right? A 3D object, right? The surface area of our sphere. Right? We're going to try to figure that out with the information given, right? So let's start by unraveling our cylinder, right? Let's say we got some scissors and we cut this cylinder right down the middle. Okay, we cut it right down the middle, right? We're gonna do that and we'll lay it out flat, right? We will get a nice rectangle. That is not off screen. One sec. Nice rectangle, right? And now, what does any of this mean? Well, let's identify each of the sides, right, and go from there. Okay. We know that this is the base. Okay. We know this is the base rolled out, and then this is the height. Okay. The height stays the same, and the base is just elongated. Okay. Now, what variables can we substitute this for? Let's see. Well, the height, right, is going to be 2 radius, 2 radii, right? That is going to be you can't see that, sorry. Height is going to be 2 radii, right? And the width, right? The width, or the we'll call it the circumference, right? The circumference of this base of this this open cylinder, right? Because anytime you look at a any circular shape, right? You have a circle, right, as the base, right? The circumference is basically the measure of the distance around the outside, okay, following the outside of the circle. So what we did is basically we cut it with our scissors and we unraveled it, and this is now our circumference, right? Which is 2 pi times r. That's not an r, that's a 2. Okay, times r. Right. Now, looking back at our formula over here, right? Let's do some simplifying, right? Let's put this in a little equation, okay? Well, I'm gonna skip ahead. Let's not put it in an equation. Let's just let's solve for it, right? 2r combined with 2 pi times r is equal to, right? Is equal to 4 pi times r to the power of 2. We have our 2 r's, our 2 radii, and the radius. Sorry, I should have explained this earlier. R represents the radius, right? And the radius is basically the central point of a circle to any point actually on the outer side of a circle, right? So the radius is half of the distance from one point to the next, right? From the center of the circle. That makes a big difference because it's not a point from here to here, right? That's not what I'm talking about. It's from one point to another on the side of the circle, going through the center, of course. Alrighty. Well, now let's look at how to get the volume. I'm going to leave this up here. The volume of a sphere, not a circle, a sphere, right? We looked at how to get the surface area of our sphere. Right? We looked at how to get that. That's this neat little equation out over here. Now we're going to try to find the volume, right? And the volume, let's get our little base, right? The volume is the stuff that makes up the inside. How much can we contain within this, right? The volume, right? Yeah, we're gonna be looking at that. So let me write out the equation really quickly, and you'll see piece by piece how to put this together, right? And we're gonna be using a nice little example. So let me write that out really quickly. The volume of a sphere is equal to 4/3 pi times r to the power of 3. Now this will make sense in a second. Now let me just explain by using this handy dandy little example this fabulous book uses. Right, so our example is that we have a sphere made up of many pyramids, right? Don't know what a pyramid is, right? Pyramid, it has a base, right? That is similar to a square. That is a square, right? And basically, its sides, right, are triangles, okay? They are triangles, right? That's what a pyramid is. And what we're trying to say is that we have a sphere, right? A sphere, right? We have a sphere, right? Looks kind of like a pumpkin, but that's not what it is. We have a sphere, right? That is made entirely of these pyramids, okay? And what we're trying to do is figure out the surface area. We're trying to figure out the volume of our sphere based on the surface area of our pyramids. How do we do that? Right? Now we need a little bit more information, right? Now if we look at our pyramid over here, right? We look at our basic generic pyramid. Okay, if I can draw one properly, right? I don't think I did that one properly. Right, that looks a little Jenkins, but we're going to consider that a pyramid. Okay, we need a little bit more information, right? So each leg length, right, is equal to the radius of our sphere, right? And I talked about what radius is earlier on. Radius is a central point, right, to the distance between the central point of a circle or a sphere to the outer point of a circle or a sphere, right? That is the radius, right? So these legs right here is equal to the radius of our circle. Now, what does that matter? What does that matter? It'll matter quite a lot in a second, right? We can find basically the surface area, right? Since we know our reference, by combining all of the pyramids together, right? And we're not using these sides. We're not using these sides that look like triangles, right? We're going to be using the base of our pyramids, right? The base of our pyramids, okay? Combining them all together to get our volume, right? To get our volume. All right, so what would that look like? Well, let me write out this confusing equation, and then let me simplify it, right? So the equation, I believe, is B is equal to, tell me if you remember this one. B is equal to 4 pi times r, right? Times r to the power of 2 over the number of pyramids. Okay. Let me explain this to you. Okay, so B, right, is base. B represents the base of our pyramids. It represents the base of our pyramids. Okay, this is we're looking at it from a top view, right? This is our base of our pyramids, okay, which is a square, right? Which is equal to, right, this little equation we used over here to calculate the surface area of our cone, right? Which in turn we found similar to the surface area of our sphere, right? That was inside of our cone, right? That's what this is right here. So base is equal to the surface area, right, of a sphere, right, divided by the number of pyramids, right, which can be represented as variable n, the number of pyramids, right, because you can't just have one pyramid. It's not going to work. You can't just have one pyramid to make up a sphere, right? You need multiple, hundreds, or however many, right? And so by using this little equation, we can find, indeed, oh, sorry, my bad, my apologies. The base is equal to all this, right? I'm getting ahead of myself. Alrighty, so let's move on to the next part. Right, let's move on to the next part of our question, right? And we're trying to figure this out. The surface area, sorry, the volume of a sphere. We're trying to figure that out based on the pyramids that make up the sphere. Right? So we need a little bit more reference, right? So the volume of each pyramid is equal to, write this out, 1/3, right? 1/3 of the base times the radius, right? Times the number of pyramids, okay? Times the number of pyramids, right? And as before, I'll write it out for you. N is represented as the number of pyramids. All right. So what do we do? Well, we plug in this little thing. We add it onto the equation we were just looking at, which is equal to the base of our pyramids, right? So let's write that out really quickly. So we have 1/3, right? 1/3 our base. 1/3 our base. We don't have to write that out. Times our equation, or sorry, the surface area of our cone. No, not cone. Sorry, cylinder, our open cylinder, and sphere, right? Which is 4 pi times the r. Sorry, not r. Well, r, but the radius to the power of 2 over n, which can be identified as the number of pyramids it takes, right, to create our sphere, okay, times the radius, which is r, and times n, which is the number of pyramids it takes to create our sphere, as defined before, okay? And if we simplify that, we get something I wrote a little while ago that you will see is the exact same. So let's bring it all the way back over here. I like arrows. You'll see me writing arrows a lot. Right? So to simplify that, we will get 4 over 3. Come on, let's write it. 4 over 3 pi times r, or the radius, to the power of 3. Right. And that right there can be defined as our volume of our sphere, right? Which is this right over here. So this is the volume of our sphere, and then this is our area, our surface area of our sphere. Okay. Okay. Now let's take a look at similar figures. Similar figures. Let me write a couple examples over here, and you'll get an idea for your own, right? Similar figures. All right. Let me draw a couple over here. Similar figures. All right. Now these figures right here. All right. What makes them similar, right, is their angles. Okay. They all have the same shape. Right. They all have the same shape. But what makes them similar, not the same, right? If they're the same, they would be the same size, right? Well, but what makes them similar is their angles, right? The angles is what makes them the same. So, right. So when you have a big, let's call this big square and tiny square, right? When you have this larger square, this big square, right? It is bigger than this little square, but it has the same angles. It has the same fundamental 90 plus 90 plus 90 plus 90 degree angles, which create 360 degrees. Right. Another thing that makes figures similar is that there is a constant ratio, right? So not only are their angles consistent to one another, it's their side length ratios, right? The circle probably isn't the best example to show that, since they don't have any side lengths, circles. But when we look at, say, this triangle over here, right, we notice that. Let me give it a quick example, right? Our angles are the same. Our angles are the same, right? And we can identify that these are similar, right? Also based on their side lengths, right? So we can say that this, for instance, this side length is 2, right? And this side length on our bigger triangle, right triangle, is 4, right? Our base to this is let's say 1. This is 2, right? There's a ratio here. Okay, there's a ratio here to each of these sides. Okay, so let's write it out really quickly. So our ratio, right, is 2 over 4, right? Which is 1/2, which is equal to 1/2. There's a 1/2 ratio between. Oh no, I'm sorry. I did it backwards. There's a sorry, it's 2. Sorry, it's 4 over 2. There is a 2 to 2 ratio in this. These two figures. Okay. All right. So, given that, let's write out a little example of this. And then figure out how to find this based on the information given, right? Knowing that, as reference, that these two shapes have and are similar figures. Okay, I'm going off of the book right now. I think it was something like, what was it? It was a yardstick, right? Something about a yardstick, right? So a yardstick makes, and if you don't know anything about a yardstick, 3 feet, right? A yardstick casts a 5.5 foot shadow, right? So the sun's up here, right? 5 foot shadow, right? Right here, 5.5 foot shadow, okay? And then there's a tree, right? There's a tree that makes a 28-foot shadow. Right, a 28-foot shadow. Okay. Right. What we are trying to figure out is how tall this tree is. Right. And now, if you don't notice it already, we can see that if we add another line in here, we get a nice little triangle, right? And another thing to look at is the sun. Oh, you can't see my beautiful sun up here. My apologies. It's out of screen again. You can't see my amazing sun. Okay, this is our sun, right? We're using the sun to base these two objects off of each other to create similar figures, because the difference between how do we say it? The light is very, very tiny, right? Very, very tiny. So we're just approximating. We're just approximating this, okay? So what we're trying to figure out is how tall our tree is. Hold up. Let me make this look like a tree. My apologies. I'm not no math book. All right. This is our tree over here, right? We're trying to figure out how tall that is. Okay, how do we do that? Well, we can put it into a nice little solution right over here, which is, I think the book had was 3 over x, right? And x is the unknown height of the tree, and 3 is our height of our yardstick, right? Is equal to 5.5, okay, which is the length of our shadow, okay, for our yardstick, over or divided by 28, which is the length of the shadow of our tree. Right. So how do we figure this out? Well, looking back at our original ratio, our original figure ratio, computing this, we would end up getting that our tree height is indeed 15. That's a 12. Okay, that's a 2. It's 15.2 something something something, right? And that's the solution we use to find similar figures, and we can do this throughout other examples as well. Okay. Now, that was just two-dimensional. I was just talking two-dimensional. Now we can get into to three-dimensional objects. Okay, this can work for 2 and 3D. Okay, so let's draw out a cube. All right, I'm slowly getting better at my math drawing skills. Hopefully, I think so at least. Maybe at least the speed at which I do it. I don't know about how the quality of these. Right. So say we have two. Oh, I did this wrong already. We have two. I did that wrong. 2 cubes. Okay, 2 cubes. All right. Oh my goodness, I forgot how to draw it. Getting tired over here. We have 2 cubes, right? 2 cubes, right? One is bigger than the other, okay? Let's say this one has lengths of 2, 2, 2, or dimensions 2, 2, 2. And let's say this one has dimensions of 10, 10, 10. Okay, let's make it a little bit bigger for reference. Hopefully it doesn't get confusing the larger I make it. All right, dimensions 10, 10, 10. All right. Now, what we're going to try to figure out is if these are really similar. If these are really similar, and we can prove that by doing by using a ratio that we did previously on, right? And so that ratio would end up being 10 over 2, right? 10 over 2, right? Which is one of the side lengths, whichever one, right? Since all these are equal, right? Which is equal to 5, right? It has a ratio of 5, right? So, what about the surface area? What about the surface area and the volume of these? How are these similar? Okay, let me put this somewhere else. We know that the ratio between these are 5, right? And we're looking at the perimeter for these ones too. What about the surface area and volume for these, right? So we know that the volume of this, right, we multiply all these together, is 2 times 2 times 2, which is 8. Right, that is the volume. Okay, so that's the volume, right? And now, how do we figure out the surface area, right? The surface area, right? And I'm not gonna write it out, but it ends up being 24. Okay, that is the surface area. Okay, I'm not sure. I think you can see that, right? And we're looking at this cube right here, right? And if we do the same thing, I can't talk. The same thing over here, right? We're gonna end up getting this cube has a volume, or yes, a volume of 1,000. Okay, and this has a surface area of I think it was let's see, surface area 600. Yeah, this has a surface area of 600, right? Now if we were to write this out, right, and make another ratio similar to the one we did over here, which was 10 over 2, which is equal to 5. That is our ratio between side lengths, okay? Now if we were to do a ratio between, say, volume and the surface area, right, we would get similar outcomes, right? So let's do this really quickly. So we would have 1,000 over 8, which is what is it? Which is no, let's do this first. Let's look at surface area first. It'll look nicer. Which we will have, okay, 600 over 24, right? And I'm not going to do the calculator work. You can if you'd like, but which is equal to 25, which is also equal to 5 to the power of 2. 5 to the power of 2. Okay, still got 5 going on for us. All right, and now we're going to look at the volume, right? Which is 1,000 over 8. Okay, 1,000 over 8, which is equal to, I think it was 125. 125. No time for calculators. 125, which is equal to, right? Which is equal to 5 to the power of 3, right? I'm not sure if you see the similarity in this, but you notice that all of our answers are 5 and increase as we go from the ratio of side lengths, from the surface area to the volume, right? Surface area to the volume. So let's write it out really quickly. Side length ratio is, if you can see, let me scoot down a little bit, 5, right? That's how we identified this over here, right? 10 over 2, that was the side lengths, okay? The surface area, right, ended up being 5 to the power of 2, okay? That's how we identified this over here. And then our volume ended up being 5 to the power of 3. 5 to the power of 3. Right. If you notice that, right, as you increased, not increased, but as you went down the ratios, so did increase the exponent, right? We went from 1 to 2 to 3, right, which I think is pretty neat. It's pretty cool. Looking at all these things, it's a pretty cool thing. Rightio. So, why does any of this matter? How can we use this to our advantage? Well, that's what these examples are for. Let's check out one of these examples in the book, pushing out of this. Okay, so say we write out another poor shape. All right, one of James' extra poor shapes. Okay, let's try to write out a hexagonal prism. Mouthful, hexagonal prism. All right, do that really quickly. Make sure it takes up the whole page. Okay. All right, and then let's write a smaller one really quickly. What we are going to try to figure out, let me write out the dimensions really quickly, but I'll tell you first. We are trying to figure out the height, right? The height and base length of our larger but similar hexagonal prism. Okay, based off of the knowledge we have from this prism right here. All right. The knowledge we have on this is that it has a height of 10, let's just say units, 10u, 10 units, just say 10, and it has a length, a base length of 4. Oh, I dropped my cap. No cap. All right, no cap. All right. Here comes the cringe. All right. So, like I said, we're trying to find the base length and the height of the larger prism. All right. Oh, my bad. I'm going off the book. I'm forgetting. I'm forgetting things. Should have these things written down. And we know for a fact that the prism, the larger prism, has a volume of 480, right, times 3 to the square root, right? We know for a fact that is the volume of our larger prism. Now, with this information, this given information, how do we figure any of this out? How do we figure any of this out? Well, looking back at our previous examples, even back to looking at spheres, you know, we're going to be working backwards a little bit. It's going to be looking like we're going to be working backwards a little bit, you know, shuffling back and forth. All right. So let's look at, let's give myself a little bit more space. Let's look at, let's see, let's look at the volume of the smaller prism. Yeah, right. We're going to find the volume of the smaller prism, right? Because we would like to find a similarity or something we can base our ratio off of, right? Because these are similar figures, right? But we're trying to prove that. Right? We're trying to not only prove that, but we're trying to figure out what the heck's going on over here. What's the height and what's the width, right? And we can do that by looking at the volume, right? And if you remember earlier on with the cubes, right? We noticed that we noticed earlier on that sorry, I'm blanking. I'm having a huge brain fart. Wow, that was brain fart. All right. Anyways, moving on. Apparently I can't remember. Apparently I can't remember what I was going to say. Let's look at first the base from an upward position, looking down on this hexagonal smaller prism to find its volume. All right. So let me draw that out real quick, because I know how confusing I can sound sometimes because I confuse myself. So let's see what this would even look like. Okay, so I hope you're ready for more poor art skills because they're coming. So if we divide our hexagon up into 6 triangles, right, we will notice that here, and let me draw my dimensions out really quickly. We don't need height in this case, we just need the base, the width, okay, which is 4. All right, we'll notice it makes a very nice little triangle, right? And if we were to cut this triangle in half, right, we would get a right triangle, okay? And it's almost similar to what we had. It is exactly, you know, it's exactly to what we had in our when we were looking at our 30, 60, 90 triangle, okay? 30, 60, 90 triangle. And let me magnify this. Say I have a magnifying glass, cool magnifying glass, okay? Magnifying, right? What we have over here is half the base, which is 4, because 2 of these triangles together make an equilateral, right? Equilateral triangle, right? So we have half the base, okay, which is 2 in this case because that's 4, right? And then we know that this is 4, right? Because that, since it's an equilateral and this is untouched, the hypotenuse is untouched. We know that for a fact that that's 4. And then we plug x in over here, and we get 2 times 3 to the square root, right? What do we do with this? Well, we figure out the volume using other equations, and that ends up giving us the volume of 240, right, times the square root of 3. Now, we have something to base our ratio off of now. We have 2 similar things to look off. We have the volumes to look at now. let's make some space. Let's make some space. We have the volumes to look at now. Right. Okay. Now that we have our volumes, right, which is 480 square root of 3 over 240 square root of 3, you end up getting a very nice, gentle number, thankfully, which is 2. Yes, I said gentle. Because there's a lot of numbers out there that do not like to be computed. Right, so you end up getting a ratio between these volumes, which is 2, right? And looking back at the cubes, right, we notice that looking at the side lengths, right, going back to having them as reference, right, you notice that the exponent is 1, right, or nothing, or it is 1, it is itself. And then you have what is it, x to the power of 2, which is the surface area, right? Then x to the power of 3, which is the volume. Okay. And now using this information, the volume, right, we are going to multiply our side lengths by how do I say this? By the square roots of this of this ratio times 3, right? So what does that look like? Again, my words can be confusing sometimes, and it's better if I just write it out. So I will do that really quickly. So we remember that this has a height of 10 and this has a base of 4 units, right? What does this look like? Okay, let me write it out. So we would end up being 4 times 3, 2, and 10 times 3, okay, over 2. All right. And that right there is equal to, and if you solve that, is equal to the side lengths, yeah, the width, right, and the height of this this larger hexagonal prism. Whew, alrighty. Thankfully we have that solved. Alright, that cleared some things up. Good stuff, good stuff. Alrighty, now we're going to be looking at my favorite shape by far, circles. We're going to be looking at circles. Alrighty, let's draw this one out. We got a circle over here. No artist, but I'm going to try my best. We have our circle over here, right? And we're going to be looking at some vocabulary right now. We're looking at some vocabulary and a little model to go with it, right? So, an angle with its vertex on the edge of the circle is called a inscribed angle. What does that mean? What does that mean? I don't like words. I like drawing it out. So that's exactly what we're going to do, right? So, an angle, right, with its vertex, right, its vertex being the opening, right, where its angle is, right, on the edge of the circle, which is right here, right, is called an inscribed angle. So this right here we're going to call inscribed angle. Okay, inscribed angle. And then this little neat section over here we are going to define as the arc angle. Okay. Now with this information, we're going to look at another term, right? We're going to look at a central angle, right? A central angle, which sounds pretty self-explanatory, but let me draw it out anyways, right? We have our circle, our poorly drawn circle. I'm running out of ink, pity. Our poorly drawn circle, right? Our central circle, which is based from the center of our circle, and its legs, right, is the length or the radius of our circle, right? Because as before, we described our radius as being the length from the midpoint of a circle to the outer, how do I say it? The outer edge of a circle. Circles don't have edges, but we're just going to call it that for the sake of description. And we are going to call this our central central angle, right? And over here, as before, we have our arc angle. Alrighty, now we are going to look at another circle. This time it's going to be a little different. What if we had 3 inscribed angles within a circle? 3 inscribed angles within a circle. Let's draw that out really quickly. See what that would look like. Alright. Let's see what that would look like. Okay. 3 inscribed angles within a circle. Alright. You end up getting a neat little thing called a triangle. Okay. Now, let's identify our arcs. Okay, well, let's first identify the angles, right? This is an inscribed angle, this is, and this is. Right? Now, let's identify our arcs, right? Our arcs can be identified, right, by each of the angles. So let's call this arc, let's call this inscribed angle A, okay? This has an arc of A, all right, arc A. All right, now let's look at this one. Let's call this one B, okay? We're going to say this has, oh, you can't see that, my bad. We're going to say this has a an arc, let's call this arc angle B, okay? And finally, we have C over here. See over here. Hope this isn't too confusing. We have arc angle B, right? Let's write that over here. Arc angle, not B, C. My apologies. C. Okay. Okay. Right. So what does any of this mean? What does any of this mean? Why do we need to know this? Well, as a reference, in inscribed angle, which is our inner ABC, which make up our triangle within our circle, is equal to 180 degrees, right? And as you know, all triangles create a 180 degree in total, right? And an arc, right, in total creates 360 degrees, right? Let's add a little plus sign just to really show you. This arc plus this arc plus this arc is equal to 360 degrees. Just how like this angle plus this angle plus this angle is equal to 180 degrees. Okay, that's basically all I am saying. Okay, so with this knowledge, we can say that 360 degrees is half of 180, right? So we can say each inscribed angle, okay, each inscribed angle is half, right, of our, how do we say this? Vocabulary words pop into head. Arc angle, there we go, is half of our arc angle, right? Okay, now let's put this, let's see what this looks like. Let's write this in friendlier terms. All right, a little bit easier to comprehend than a bunch of scribble lines from poorly drawn a poorly drawn hand. Okay, let's draw yet another circle. And man, I'm so sorry, by the way. This video is painfully long. I really am sorry. I hope you just need to skip through this video and find what you need to find. I hope you don't need to watch this whole thing because it is terribly long, and I really am sorry, but I don't know how to make it shorter. I'm just now noticing that we're reaching, what is it, 44 minutes. Wow. Time flies when you're having fun. All right. Okay, we're looking at our inscribed angles, and we just talked about how half, right? We talked about how the inscribed angle is half of our arc angle, right? So let's draw that out real quick. Our inscribed angle, not our central angle, right? Central angle is at the middle, center, right? Our inscribed angle, right? We will let x be identified as our inscribed angle, which is this right here, right? Which is half, 2 is, well, it's half of our arc, right? X. Okay, so that's how that can be identified. That is how that can be identified. All right. Let me draw a little nicer. Let me draw a little nicer for the sake of our next little fun project example we're going to be doing. Okay, now, what if we make what if we have this line? Let's say this line is going directly through the center, right? Let's say it's going directly through the midpoint or center of our circle, splitting it exactly in half. In this case, it's not because I have poor drawing skills and I don't have a ruler, but let's say it is, okay? And it's intersected by a chord, right? I'll go over what a chord is soon, right? I'll go over right now. A chord is basically cancel. Sorry, technical issues. But a chord is basically one point on a line to another point on the line, right? Not the radius, not the midpoint, right? It's one point on a line to another point on a line, right? That connect each other, right? Let's say we have a chord that connects the top of our inscribed angle, right, to the center, right? Or not the center, but to right there, right? We know for a fact that all straight lines, you can't see that, but all straight lines equal 180 degrees, right? So that's what we have right here. This is equal to 180 degrees, okay? And we will use that in just a second. Okay, let's identify our inscribed angles, right? Like I said before, our inscribed angle is half of our arc angle, right? So that would end up looking like this, okay? And we end up making another inscribed angle over here, right? We're gonna call that x as well, x over 2, right? That makes this thing over here, okay? And so what we're trying to find out is this angle right here. What's this mystery angle? Well, based on our original information given, our original 180 line, right? We will basically do a very simple procedure that we've done many times before, which is about positive, by subtracting, right? Well, actually, by first adding these two together, right? These two angles together, right? And then subtracting from the total, right? So it'd be x over 2 plus x over 2, and then it would equal whatever that equals, and then you would take this and subtract it from 180. Okay, or sorry, 180 minus whatever you get from here, and then you would get your mystery angle. Alrighty, now let's see what is next on the agenda. I already talked about chords. I think I did at least. Alrighty, sorry, I'm back. My phone decided to not work or exist anymore. So I have to act quickly. I only had a couple minutes left anyways, but I keep on running out of storage. That's the downside having technology, I guess. But I guess I wouldn't be able to record otherwise. All right, let's get right back into it. I already discussed what chords are, right? Chords are basically points on a not circle, a circle, right? Points on a line that create a line, right? It doesn't have to be through the center, right? It could be anywhere, okay? Anywhere. That is what a chord is, okay? But let's do a little example, right? Let's say we have our circle, okay? Our circle. Let me draw it out really quickly. Say we have our circle, and what we are trying to find is very similar to what we were looking at earlier before. We are going to try to find the missing angle measure. All right, so let's say we have a couple chords, right, and a couple intersecting, inscribed angles, right? Let's verify, or not verify, let's identify these inscribed angles really quickly. Let's call this one B over 2, right, because we put it over 2, or Yep, correct. Under 2 because it's half of its inscribed it's half of its arc, right? Its arc being B, right? This one we'll call A. Okay. So I know it's a little silly, but the shape is at least. Right, we're gonna call this A. All right, these are in degrees, right? And what we're gonna try to find, right, like we did before, is the missing angle. How do we do that? Now looking back at previously what we did, right? A straight line through the center, right, got us 180 degrees. We know it was a straight line, no curves in it, right? And so we could we subtracted 180 degrees minus the minus these two inscribed angles, right? These inscribed angles, and that's exactly what we're going to do here. Right? It's exactly what we're going to do here. Okay, now you get the gist of that. You get the gist of that. It's pretty simple stuff. And if you don't get it, and I didn't explain it well enough, then I apologize. Please, please tell me next time we see each other. Next, we're going to be looking at, and finally, our last vocabulary word, our last little section in this in this section. We're going to be looking at a thing called a secant. Secant. I had a hard time with that word. But basically, a secant. If we draw another circle, yet again, our last circle, I think, for today, tonight, for me. We draw a circle, right? Basically, a secant is a line that begins on the outside of a circle, right? So if we have two intersecting seconds, right? Two intersecting seconds that begin on the outside of a circle, right? Let's identify first, actually, what we have. What we have, right? So we have, we potentially have our angle right here, and we also have our arc. We also have our arc. We'll call this A, right? But we also have another arc, right? And that can be identified right here as B, right? We'll use that as degrees, right? And what we're going to try to find is the angle measure of this intersecting, this angle measure between these two intersecting seconds. All right, let me write that out really quickly. Secant, weird word, and poor handwriting, so double whammy. All right, so how do we figure this out? Well, like we've done in previous examples, we're going to be using 180 degrees, right? And to do that, we need a straight line and a triangle, right? So how does this work? How does this work? First off, let me redo this because I didn't do. Actually, for the sake of time, let's just back it up a little bit. Not that I think that would matter really, but let's do that. Okay, let's do that. Let's say the super elongated triangle has some meaning behind it. Okay, right? We're putting a chord between two of the ends of our circle. The circle doesn't really have an end, but we're gonna say so for the sake of this example, right? And like I said before, what we're trying to find is this angle right here. What is this angle of these two intersecting seconds? And what we're basically going to want to do is do what we've been doing before, right? We know a triangle is made up of 3 angles, right? We're going to try to find the difference between the angles that we can identify, right? We are going to look at the inscribed angles that our new chord created, okay, which is over here, right? Over here, as well as over here, right? We're going to be looking at those and how they play in this, right? And we're going to use our 180 degree line, which stretches right here. We're going to say that's our reference, 180 degree line, right? And we're going to subtract that, right, from what is it? we're going to say a, since this is arc a, we're going to say this is a over 2, right? We're going to subtract 180 from our inscribed angle, okay? And then we're going to add that together with our other inscribed angle over here and subtract it from 180, right? To figure out finally what our missing second um, intersected angle is. Whew. All right, that took way longer than I wanted it to. I thought it was going to be actually faster than the last video, but apparently not. It ran a little bit more smoothly than I expected, but I did spend quite a bit of time on this. I just want to say thank you if you took the time to watch this entire video. I think I said this earlier on in the video. I apologize if you had to watch this whole thing, if you were clueless throughout the entire thing. I really want to stress the idea that, you know, examples are key. For me, at least personally, I can't learn with just formulas. I need examples. And I hope these examples were sufficient enough. I got it from the book, but in the future, and I don't think, I don't have any more math sections, but in the future, I will be changing a couple things, so it will run better. But at saying that, as our incredible instructor would say, have a great, grand, and glorious day. All right. Thank you.